Hi, it's Teardown Tuesday time again. Quite a few people have been asking for this one for quite some time, so we eventually got around to doing it. It's the Jaycar MP3090 40 amp 15 volt bench power supply. It's also rebadged as the BK Precision 1692 and under a whole different one hung low names on the market. So you can pick it up pretty much anywhere. It's not a cheap power supply. It's about $340 Australian and US, I think, if you get the BK Precision one. But its main claim to fame, 40 amps, output at 3 to 15 volts variable. Only a single turn pot, not that exciting. Voltage and current displays, there's no current limiting. It does have the capability to have a fixed 13.8 volt output for ham radio gear and stuff like that. But yeah, on off switch, adjustable voltage, and that's it, but huge current. And the thing only weighs about 3.5 or 4 kilos tops. So for all that current and power, if it was a linear supply, of course, it'd weigh a ton. But this one's not. It's switch mode. So let's crack it open, see what's inside, because, well, it's just a high current switch mode power supply. Could be interesting, or it could be boring as batshit. We'll find out. And of course, its specs aren't going to set the world on fire. 10 millivolts output noise, like over 200 millivolts load regulation, things like that. But it does have that 40 amps. If it does do 40 amps at 15 volts, I'm not entirely sure if it does over the full range like that, but certainly 40 volts at lower voltages. We're talking, 600 odd watts capability from this thing. It's not bad at all. But yeah, I know PC power supplies do that sort of thing, but this one I expect to be a bit better built than your average, PC power supply. But only one way to find out. Take it apart. Alright, what are we expecting inside this thing? Well, as is typical with PC power supplies, and most power supplies in general, really, they're pretty much going to use a single-sided PCB. So I expect a big single-sided switch mode PCB with some heat sinks on it, all through-hole construction, of course. A couple of front panel boards for the display and stuff like that. So let's check it out. Oh, what have we got here? Way, yep, there we go. Bingo. And the first thing you notice is it looks well built and well constructed for a typical single-sided switch mode power supply. I like it. But what I found down here in this little section down here is the manufacturer and the manufacturer's model number. And there it is, Manson. 4520 doesn't seem to mean much, but if you Google Manson 8400, you also get the Manson 9400, and I was able to pull up a full service manual for it. You little ripper! So I hadn't heard of Manson before, but it turns out they're a Hong Kong based company who specialise in power supplies. So it looks like this is a reasonably well designed, it's not a slap together bit of kit. And in the service manual, not only has it got instructions for how to calibrate and test it, it's got a complete component overlay, matching bill of materials, and most importantly, the schematic. Awesome. So inside this thing, the basic operation, we'll look at all the individual components in more detail in a sec, but the basic flow here is mains input here, we've got some filter in here, we've got it going over to the front panel main switch here, comes in here, we've got some more filter in there by the looks of it, we've got a bridge rectifier under there, and got a couple of more caps, and then we've got a couple of transformers which couple over into the low voltage circuitry over here, and then we've got our main switch-in transformer here, we've got a big inductor up here, you can tell because it's only got the 2 wires coming out of it, another big fat inductor here, a couple of diodes on this heatsink for the output, and some output filtering, and Bob's your uncle. So let's take a look at each section in a bit more detail. And here's our IEC mains input here. There is no voltage switching. It's 240, specifically designed for 240 volts. We've got a MOV here. It's actually heat shrunk in a bit of heat shrinking. Excellent, right on the terminals, exactly where it should be. This, interestingly, goes into a little board holding nothing more than an 1 microfarad input filter cap. Once again, it's got all the necessary UL and all the markings on them. Check them out. There's a million of them, and there's a bleeder resistor in there, a tiny little one in parallel, and that uses a connector. It's actually glued down. You may not be able to see that in detail there, but it is actually stuck in place. It's excellent. We've got heat shrink over the terminals, heat shrink tubing. We've got heat shrink tubing over the earth terminal here, and the earth terminal goes down to a shake-proof washer down on the chassis down there. Excellent. And then it, as again, interestingly, goes into a filter can here, and we'll take a look at the circuit for that. That'll just be a pretty standard mains common mode filter. And the output from that, of course, they've got earth coming out as well separately on the output side. Once again, heat shrunk, cable tied, brilliant. And the output from the filter, once again, it's heat shrunk all the way over. That goes into your double pole main switch on the front panel. It's got a real clunking main switch. Once again, properly heat shrunk, cable tied, going over to some PCB spade terminals over here. Once again, heat shrunk. Beautiful. And here we've got an NTC thermistor, more filter in here, another huge filter cap. Once again, they really haven't skimped on the components. We've got a common mode filter here going over into the bridge rectifier. And there's the bridge rectifier. They've put a little heat sink on top. I love it. Little tiny plate. They obviously decided that they needed just a little bit more thermal dissipation there. I love it. 3.3 microfarad high voltage caps, 400 volts. Haven't skimped at all. Now I was wondering what this transformer here is and this little bit of circuitry here until I checked the chip against the schematic, and I found out that this is a power factor correction. It uses an MC Motorola MC34262 power factor correction device, and that's part of the transformer and the circuitry used for that power factor correction. So they've gone to the effort to actually do that. I think that's brilliant. And check out the copper strapping shield on there, and it's around the transformer, and they've got those on the other transformers inside as well. Nice attention to detail. They've gone to town to ensure that this design is actually going to meet EMC requirements and things like that. Now let's actually take a look at the schematic and follow the circuit up until this point, because I don't want to get carried away and then show you the circuit later. So we'll do it step by step, I guess. And there it is, Manson Engineering Industrial Co. It dates from 2002, Rev 1.6. Now this is for the 9400 model, but apparently the 8400 model that I've got here, well, presumably is exactly the same. But even the 9400 model, the service manual shows it's branded 8400 on the overlay diagram. There it is there. So go figure, like 8400, and that number matches my PCB precisely. But anyway, here's our input here, here's our MOV, there's our parallel bleeder resistor. You remember that cap and that resistor were on the board, the MOV was on the IC input connector. There's another NTC there, and there's the inside, the filter, that filter can, which we saw inside the unit there. And that brings us to our mains power switch on the front panel. There it is there. Once again, another bleeder resistor, 2 inductors, a mains rated filter cap. There's our common mode choke there, another filter cap, and there's our full wave bridge rectifier that we saw that had the heatsink on it. And that brings us on to our MC34262 power factor correction circuit we saw. And there's the big transformer we saw there. It's a little 8-pin dip chip, and all that does power factor correction. and then it goes through this diode here into the main filter caps. And as we saw in the previous Xantrex teardown video, we also, these are series caps like this, once again with the voltage sharing resistors across there. So we get our high voltage DC across here and here, which actually goes down to, if you follow those wires down in there, it goes down to our main switching transformer down in here, which we'll take a look at. But of course we need a little power supply here to power the circuitry on our main board, and that's what TR2, this transformer here, does. That just powers VCC. There it is there, through some filtering, a small rectification, filtering, and an inductor, and another filter cap. That's a VCC for our circuit. So if we take a look at our board, we'll be able to find TR2, and that will be bridging the high voltage part of the circuit with the low voltage part of the circuit. And that's pretty easy to find. There it is there, because you see this black line going through here. They've got this black line on the silk screen, which actually separates the high voltage and the low voltage part of the board, and it's got a high voltage warning. Not sure if you can read, but there it is, high voltage section. So all the stuff in here is no touchy, really. You can't see the black line, but it goes in between there, and there's our there's some switching transistors in there. But that is, there it is, TR2, and that separates. See, the one side here is on the high voltage section, and the other side is on the low voltage section. And there's another transformer which does a similar thing here, bridges high voltage side with the low voltage side. And that transformer I just showed you is TR3 here, and that actually comes, that is actually the driver for the PWM controller, and it's a Texas Instruments TL494 PWM controller IC, and that drives the two switch-in MOSFETs here, Q12 and Q13 here, to drive the main transformer, which then gives us our DC volt, our main 40 amp DC volts out. And if we take a look at the TL494 pulse width modulator control chip just very quickly, it is actually a PWM controller, fairly generic one. It's not actually a switch mode voltage regulator controller as such. It's you can use it for quite a few things, but it is one of its primary uses is for a switch mode power supply application. And if we go down here and take a look at the functional block diagram here, you can see that there's not much in there at all. There's a voltage reference down here, an internal reference. There's a couple of error amplifiers that are summed there. There's an internal oscillator, switch-in oscillator. There's a deadband controller, and there's a steering flip-flop, and some output, some uncommitted output transistors, so you could use them in various configurations if you needed to. So there's really not much in there at all, so it is fairly generic, and you would have to look at the greater operation in terms of the actual schematic for this device to see how it's better used. And there's a typical application circuit, and as you can see, they don't tell you what the outputs go to, because you can have your own configurations and use them in various configurations. And as you can see, it changes its pulse width to actually match the various waveforms dependent upon the threshold voltage and the feedback on couple of pins there. There it is, DTC and feedback, and that's pretty much all there is to it. So if you wanted to go through it, you would have to have a look at the main power supply schematic and see how it integrates with this pulse width modulator controller and the driver transformer and things like that. Well worth looking into. So Q12 and Q13 there, they're our driving MOSFETs, and they're on a big heatsink in there, which I'll show you in a second. And as I said, it comes from the high voltage DC section up here. So here and ground, of course, it looks like there's a second, but there's a second wire coming from the center tap of these caps here. And interestingly, that goes through, is AC coupled here, through to the other side of the transformer like that. So it's switching between the positive rail here and the negative rail, and the center tap for this side of the winding on the transformer, and the other side of the winding on the transformer is connected, AC coupled, through to the center tap of those two main DC filter caps. So this here, TR4, it's the biggest, it's the big transformer, so it'll be the biggest transformer in this box, and we'll find it in a second, and it's what transfers all of our power across. These other transformers we saw, like the driver transformer here, is only a small fry. It's only transferring control signals, and the other one we saw up here is only doing sort of, low current stuff to power the low voltage circuitry. But this is the big beast where all the power gets transferred, and then we get rectified over here, filtered, and it goes through to our output, which we'll take a look at. But let's try and find these big power devices on the board. We've got a bit of Chinglish happening here. Caution! Warning, Will Robinson! Touching may hurt you by high voltage! Exclamation mark. This one may be a bit hard to see, but there's the two switching MOSFETs, Q12 and Q13, down in there on their own heatsink. So I've actually got three heatsinks in this thing. Here's Q12 and Q13, the driving MOSFETs down in here. That's the smallest heatsink in the bunch. This big thing here, as we'll take a look at, is the output rectifier diodes. And then this one up here is the MOSFETs for the power factor correction circuitry, which we saw before with the power factor correction transformer and the controller chip hidden in behind there. And you can see those side-on output rectifier diodes, drive transistor MOSFETs, and power factor correction MOSFETs. And I don't think I actually showed those before. There's the two, Q1 and Q2, the power factor correction MOSFETs there. And I stand corrected, there is a fourth heatsink in here, which is the diode D2 here, because it does transfer effectively all of the current through it for the entire supply. So that is inside here somewhere. Where is it? There it is. Tiny little puppy down in there. And I just thought I'd mention the fan driver. Yes, it is temperature controlled, and there's the LM324 control circuitry to drive that. And as part of the PWM circuitry, they got some dedicated over voltage protection as well. That's just to stop the output voltage going berserk if there's any component failure inside this thing. And I almost forgot to point out our esteemed main switching transformer. There it is. It's the biggest transformer in the thing. Here's the switching MOSFETs on there, heatsink down in here, and that drives the output. As you can see, fairly thin wires going in relative to the high current output. Huge, big, thick red and black ones there going into the output diode, and these two inductors, which we'll take a closer look at. So how does our output rectification and filtering works? Well, it's pretty basic, and you'll no doubt recognize this. There's a few extra components in there, but the basic topology is a center tapped full wave rectifier output. Here's the center tap, which goes through to ground. Just ignore all those resistors. That actually goes through the grounded output. The current sense, we'll get into those, but there's our center tapped ground output and our two diodes here and here, but there's actually four of them. There's actually two in parallel there and two in parallel down here, and of course they're carrying the full 40 amp output current, so they need to be heat synced, and we've had a look at them, but we'll take another closer look. They've got some caps across those. We've got an output filter inductor here, an output capacitor, another output filter inductor, and once again these two inductors need carrying the full 40 amp output current, so they need to be big beasties, and they'll stand out like dog's balls on the PCB. Well, you've probably already seen them there. And we've got our output filter in here, some caps in parallel, and we've got 12 0.1 ohm resistors all in parallel here. It looks a bit weird, but they're actually flip this up to here, and that one's in parallel with that one, that's in parallel with that, etc. So there's actually 12 total 0.1 ohm resistors in parallel, and that's current sense, which is actually tapped off here and goes up to our current meter here and off to some other circuitry over there. And we've got some extra caps in parallel here. They'll be on the separate output connector, and they go to chassis earth ground. You'll note the the chassis ground symbol as opposed to circuit ground. Chassis ground and circuit ground aren't necessarily the same thing, and that will be for extra RFI compliance and filtering. And the main output filter, and they're not skimping here, they've got 2,000 microfarads in parallel and different values here once again for filtering the different frequencies. These will have different ESR at different frequencies. And we've got a 1 kV cap here and a 330 ohm 1 watt bleeder resistor, so when you switch this thing off, it drains the voltage or bleeds the voltage off the output filter caps very quickly. It's a nice touch, and it's things like that which separate the cheapy supplies from the good ones. So here's our main switching transformer up here, and you'll see the huge, big, thick, heavy red and black wires coming out of here, soldered on to the main board down in here. And here's our two bridge rectifier diodes in here, and here's that big output inductor which you saw before. But where's the other output inductor, I hear you ask? Well, it's this sucker over here. Look at the beast. And once again, it's strapped for shielding as well. Beautiful. And once again, huge, because it's got to carry the 40 amps, huge, big, thick cabling. Once again, heat shrunk, done it very professionally. I love it. Now this here may look a bit bodgy, these terminations, but they're not. That's reasonably common. There'll be like a little splayed terminal under there mounted onto the board, which then they solder directly onto the top. So it looks bodgy and blobby, but it's not that bad at all. And here's our output current sense resistors here, which allows us to read the output current. And if you're wondering what these big metal things are, they're huge, big jumper links. Effectively, that's what they are, because they can't rely on just the PCB to transfer all of the huge current from this side all the way over to our output wire in here. They use these big, thick metal shunts to transfer all the current, so it doesn't have to flow through the copper on the board. Other small touches in here, this capacitor is actually glued down, as are all the other main capacitors in here, and the same can be said for some of the inductors here, the common mode chokes, and these caps. They're actually gunked or glued down as well to stop vibration during transport and use for these things actually shaking loose and breaking off. Nice touch. They've put, you know, a lot of effort into actually designing this thing properly, not just designing the circuitry, but actually the physical build as well, which is what will set a good quality supply apart from a low quality one, which, you know, this one might last 10 years, and another one hung low brand will be dead after a year on a trolley being wheeled around in a production environment or something like that. Another small attention to detail, the main output inductor here has actually got these metal plates to hold it down, and so is the main transformer. They haven't relied on just the transformer itself. They've gone to the effort to put a plate there, the bolt through, and a shake-proof washer on the underside of the housing. And there's our 40 amp output wiring going over to huge, probably might have to get a different angle on this one, but it goes over to the big spade terminals mounted on the front panel. I've had to go handheld for this one, but you can see the huge big 40 amp red wire there going into the big crimp terminal onto the big nut and washer there on the front panel, and they're the two, you can see the black one as well, they're the two front panel output terminals. And you should be able to just see those two disc ceramic caps under that heatsink there. They're on the filtering on directly on the front panel PCB. They've actually got a small PCB there that mounts those two output binding posts and terminal lugs. And really, there's not much else doing on the front panel. There's the single turn voltage pot on the front panel. It's got its own board, our output display, voltage and current display with its own regulator there. Once again, it's glued down to the top board there. That's a little bit bodgy. It's at a different angle. I think they kind of maybe didn't have enough room left over. It sort of seems to be wedged in there like that. But apart from that, there's not much else doing on the front panel. There's another tiny little board over here for the LED indicator on the front panel, but that's about it. But there is one thing left on the front panel, and you'll see that high voltage cap there connecting the circuit common output through to the chassis ground. And as far as the main PCB goes, you've got a couple of single turn trimmer caps in there for tweaking this thing, and you'll notice that there's a switch here, switch 2, which actually is inverted, and it goes through to the switch on the back panel, which is the selectable 13.8 volt fixed output, and it's warning you as the 13.8 volt is selected, the front panel voltage control is disabled. Well, duh, of course you'd expect that, but warning. So overall, what have we got here? Well, we've got our 240 volt mains input here, some filtering, full wave bridge rectification here. We've got our power factor correction magic happening here. We've got our main high voltage filtering that branches off into over to here, which powers via a isolation transformer, powers some low voltage circuitry, like all of the low voltage circuitry basically, and it branches off down into here like, well, this, here we go, and it also taps off down into here into the main conversion transformer here, which is controlled by this driver transformer here, which is controlled by this pulse width modulation controller, which actually controls the output voltage of this transformer. And then we've got our full wave output bridge rectifier here. We've got some some filtering there with the inductors, and then we've got our main output filtering going off to our output terminals over here. And that's pretty much all there is to it. There's some reference type circuitry stuff up here and over voltage protection and fan control and then some other stuff happening around there, but that's the basic concept of it. Check out that squiggle. It's got to mean something, surely. So there you go. There's the Powertech Jaycar MP3090 or BK Precision 1692 or whatever brand, or it's actually manufactured by Manson in Hong Kong. It's the SPS 8400/9400 40 amp 3 to 15 volt switch mode power supply, and it's really well built. I was thoroughly impressed with that. I couldn't really fault the thing. It's got everything you would want in a switch mode power supply. A lot of attention to detail. Very well built. I love it. Highly recommend this thing. But it's on the pricey side. You know, as I said, it's well over the $300 mark. Maybe you can pick it up cheaper than that on the street. But yeah, it's built really well designed. And I'll have the service manual with the schematic and the parts list and everything else linked in the video there, so I highly recommend checking that out, and also those data sheets as well, so for the main controllers, because these are fascinating things how they work. So it's definitely worth some bedtime reading there. So there you go, that's Teardown Tuesday. If you like it, please give the video a big thumbs up on YouTube, because it really helps a lot. And you can, as always, you can discuss this in the EEVblog forum. Catch you next time.